lot more to achieve. And basically, what is an inverse problem? An inverse problem is a problem like the following one. Can we get a density of the Earth, which is not a directly measurable quantity, okay, from the Earth's gravitational field, for example? That's an example of an inverse problem. Now, all such problems can, in fact, be approximated by iterative procedures. And these procedures have all of the problems associated with them. They have non-convergence, they have slow convergence, they have convergence to local minima, they have stagnation, external parameters such as noise affect each and every one of them. Now, if you want to experience an inverse problem, this is an inverse problem. Basically, what you are seeing are two solutions. And you don't know whether it's in or it's out. This is a very famous illusion. It's called the Necker illusion. And basically, a neural network in your brain is actually acting in such a way as to really try and iterate the solution. So you're seeing all of the problems. Non-convergence to a particular minimum, slow convergence, convergence to a local minimum, stagnation in one minimum, and if you start blinking your eyes, you will see that the in and out image will actually be faster. So it's actually sensitive to noise. So inverse problems are one of the most important in science and mathematics. And there's a long list of them, and I won't bore you with them. They're pervasive. They're usually ill-posed problems, which means that you need to, in fact, add information in order to get to the answer more easily. A classic inverse problem is imaging. Okay? There are two aspects of that. One is phase imaging, and one is super resolution. Other examples are this. You see this beautiful structure of a protein. Actually, the way in which it was originally solved was attacking the inverse problem of X-ray diffraction. And the man who did it, people don't remember him. In my physics classes, I usually ask who is John Bardeen. They don't know what he did, okay? Even though he won 2 Nobel Prizes in physics, okay? But in any event, the bottom line is no one remembers who Perutz was, and he was a genius. He was given the problem to solve a crystal of hemoglobin by his advisor, who was William Bragg. So Bragg came back from a trip to America, and from Sumner's lab at Columbia, he picked a crystal out, and he gave it to Perutz, who in 1935, okay, and said, now solve this. At that time, sodium chloride had been solved. Well, it took a long time for Perutz to solve it, okay? And I'll explain what I mean by that in a minute. But the two aspects of the imaging problem, super resolution, we all know about the Rayleigh criterion, okay? We all know about near-field optics, okay? And we also all know about near-field optical probes. But what really near-field optics has done is solve two problems, both the super resolution and the phase problem, as we've heard several times in these talks. And here is a beautiful example. This is the propagation of a wave in a silicon waveguide. And it gives you both the 3D structure, it gives you the intensity, it gives you the phase of the propagating wave. And when you have both the intensity and the phase, you can backpropagate a wave and find out even what was underneath the surface from which it came. So, in spite of the advance of such 3D imaging, all these modalities, okay, whether it is near-field optics, whether it is SPARM or STED, they all suffer from the same thing, and they all suffer from something that the simplest optical microscope doesn't. And the problem is speed, as the gentleman there pointed out in one of the talks. So a lens can get in parallel a full image at the same time, but no 3D or super resolution. And besides the intrinsic excitement of reaching a previously unachievable goal to achieve this directly, the fact is that you really want to also achieve speed in measurements. Because there are many measurements. I've been to many places. The first question they ask is, how long does it take? Okay, and when you tell them it takes, whatever, it's not very nice. So the bottom line is that what we want to do is to have an exact global minimum solution without iteration in parallel to obtain phase and super resolution. Okay, so we need to address the problem of how you solve the inverse problem of imaging. So the question is, how did Perut solve it? Okay, and Perut solved it by a specific technique. He basically realized that there is no phase in this X-ray photograph, and he obtained this beautiful image of hemoglobin. And in his obituary, it says what he really did, okay? He used heavy atoms to solve the phase problem in 1953. So just remember, that was nearly 20 years after he got the problem for his PhD thesis. A war intervened in the middle, so it was okay. But in any event, what a heavy atom replacement means is you put a heavy atom on one of the points of the protein, and so long as it doesn't change the phases, that means the positions of any of the other atoms, then you can get a difference of the intensity of this heavy atom, okay? And that's in real space, or in reciprocal space, you see those regions which have been changed in their intensity by the heavy atom, and you get what is called a difference Fourier map. So actually, optical imaging and X-ray diffraction are very, very closely related, okay? Because what you see here is you see the scattering of these X-rays, and it's a Fourier transform, which has a phase term, it has amplitude term, but what you're really recording is the square of that, so you actually lose the phase term. And then you can do an inverse transform if you want. So this is the square of that function over there. And in optical microscopes, you see that same square at the Fourier plane of the microscope. So our development of near-field optics really, both in concept and in practice, gave us an opening to emulate Perut's and solve the inverse problem. So we all know it. Here's a probe. Here's an instrument that can in fact be completely free in its axis without having any blockage of light such as occurs in normal AFM probes. And basically you can place it anywhere on an image and take a CCD image of that. So an NSOM probe is an ideal heavy atom. It is a delta function, and it can be added to any type of sample, and it can be moved around, that's very important, nanometrically, with AFM, and you know exactly where you're moving it, okay? So the idea then is to use NSOM as a heavy atom in optics. But that's not enough. That's just an idea, okay? The idea has to be actually implemented with an algorithm, okay? And we searched around for many algorithms, and we failed, okay? And then a new PhD student came to my group. Her name is Daniel Honigstein, okay? And she said, you know, I'm going to give this 6 months. I'm going to check and go into the library, and if I can find an algorithm that even comes close, I'm continuing. If not, I'm leaving your group, okay? So we said, fine, that's no problem, okay? And one day she comes back with this paper, okay? And this paper is a paper published in 1990, basically not referred to for 20 years, okay? And it says phase retrieval using 2 Fourier transform intensities. So as soon as we saw that title, we said, this is very interesting. And then, to our surprise and shock, we went into the paper, and this is what they said. In X-ray crystallography, for example, the diffraction pattern of a crystal is related to the electron density distribution of the crystal by a Fourier transformation. Since only the intensity of the diffraction pattern can be measured, in order to determine the structure of an unknown, it is necessary to derive phase information. It has been observed, however, that the introduction of known heavy atoms, okay, so this was really an algorithm. It was done without any simulation. It was published without any simulation. So we didn't really know if it really worked, okay? But we were willing to try because this was amazing to us. So we now show that the algorithm in fact works, and it can in fact be put into practice. So how do you do such an experiment? You basically, and I won't use the term holography till later, but holography is a very powerful technology, okay? And it's going to be more and more important in near-field optics, I believe. And here is an example of the use of it, but I'll only come to that later, because really you should concentrate on this being used as a heavy atom, okay? So you take a laser, you split it into 2. One goes through our NSOM probe, and one goes through a collimator which illuminates the whole sample, and then you actually measure in the, you take the Fourier plane, and with the lens you put it onto a CCD. You can also take a tube lens and make an image. So you can have both the Fourier plane intensities, and you can have the intensity that will give you the image. Of course, the image is a 2D image. So if you had, let's say, a photoresist where you did something to it, you wouldn't know if there's a valley over here or if there's a hill over here. All you'd see is some index of refraction difference at some point, and you'd see a 2D image. Now I'm going to very quickly, and it's very simple, so please follow with me, okay? You have a field, X and N, and that's the sample. Every point is defined by M and N. You have a reference, which is the heavy atom, which is at this point over here. And you have the sum, which is X plus H. All of this you know. You can do the Fourier transform of this, the Fourier transform of that, the Fourier transform of this. You still know everything. You can take the square, and only now are you at the Fourier plane and what happened in terms of the intensities that are seen in the X-ray crystallography pattern. And then you can do an inverse transform, and you can express that inverse transform in this format. So all of this is known, and then you can put it in this format, as I said, and if you take these inverse transforms, so you have Ry, the inverse transform, Rx, Rh, and then there's a cross term. But you don't know the cross term. because you don't know h. Okay? So now, placing that equation over here, but placing all the things we do know, we know Ry, we know Rx, we know Rh, we don't know this. But what's critical is that h is a delta function, and therefore you can replace h by simply the amplitude. And so basically what you have is the image, that's the real image, the complex conjugate, and that's Ryxh. Okay? So you get two images really. You get, like in holography, the image and its complex conjugate, and then you just copy the real image, and that's your answer to your solution. So here it is in diagrammatic form. So this is the real part, this is the complex conjugate. So you can easily restore the real image just by what you have over here. So this is what it looks like. You have the point source here. You have these two things, and you have a grayscale image, which is here, and you have a region here, and you can see the real and the complex conjugate. And you can, of course, put it as a 3D structure, okay, like an AFM. And you can even look at the sidewall and check it versus the AFM to make sure that you actually got the right result. Or you can take a red blood cell and get a dip of 200 nanometers, even though you're using a lens of only 0.45, our 50x objective that all of you use, okay? Actually, it's easier than X-ray diffraction, because in X-ray diffraction, and I went around when I first had this paper, because I couldn't see from the paper why in X-ray diffraction they needed 2 heavy atoms. And it was not obvious to me that we needed 2 heavy atoms in our computation. And what we found was that, in fact, in X-ray diffraction, there is a very big problem, because there's an ambiguity in the sign, and they cannot tell the phase angle in the case of X-ray diffraction. So you need 2 heavy atoms in order to define the direction. So the analogy to crystallography is you have the optical heavy atom, you have the optical Fourier transform, which is the X-ray diffraction, and instead of what is called the Patterson function, you have this difference autocorrelation. Okay. However, there is a problem. The problem is right here. There's an overlap region, and I've sort of tricked you guys over here, and the ladies in the audience too. And that is that I've put a point source right at the edge, such that the overlap region is not very, very terrible in this particular case. But even though there are algorithms there is an algorithm in this paper to get rid of this region. It's iterative, and therefore, unlike the rest of the paper, which is not iterative, and therefore it's sensitive to all the things I mentioned previously. But what's very interesting is you can move your probe, say 100 nanometers, and the overlap between the 2 images will change. So you have the ability to achieve multiple imaging without moving your sample, just moving your probe, say 100 nanometers, knowing how much you move the probe, okay? So the bottom line is that when you have multiple images, it's well known that the greater degrees of freedom you have, the better resolution you can achieve, okay? So what you see over here is exactly what I just explained to you. However, the problem of the algorithm can be solved. And that's what this workshop is all about, okay? It can be solved with 2 probes, okay? And let me explain, not for the same reasons that, that Perutz needed 2 probes. But let us say that we have a sample. We can break the image into 2 parts and first solve one part and then solve another part. Specifically, you don't need 2 probes. You can actually use 1, but 2 make it much easier. Okay. So if you put your reference source here, then you can solve this part, and you get it very well, and you can't solve this part, which is overlapped. Okay. On the other hand, if you put your reference source over here, you can now solve that central part here, but you can't solve the other part very well. So you have an ability with 2 probes to do that. And here is what it looks like with 2 probes. And here is the actual computation. Because you can even see that the computation has shown you the 2 probes and has calculated for you the phase of those 2 probes. So what have we accomplished? We have accomplished a parallel solution to the phase problem, okay, with no added parameters. It's an exact solution, okay? And we even get a starting function. That means that's the image that we can get at the same time. So we have a lot of information. And once we know the amplitude and the phase, as I mentioned, we can backpropagate the wave even into the depth of the sample. And as we said, as you move the probe, you get multiple images, which allows you to get a thing called oversampling in imaging. But it also has super resolution potential, but this has not really been shown up to now. Because you know the exact movement of the image relative to an exact movement of under 100 nanometers of the probe. So the bottom line is, in the future, this will certainly allow us to solve that problem, I believe, in a more, and achieve super resolution. We haven't done it so far, okay? And you also have the phase ambiguity problem solved, because depending on where your probe is, if it's higher or lower, at the same point, you basically can solve exactly the phase ambiguity because you know how much you moved it with an AFM, okay? And we think that this should also, in fact, allow us to apply it to electron microscopy. There's been a lot of interesting, work done, and this is one of the most recent papers that is also iterative to get the phase in electron microscopy. And we believe that this should be a better case where you have a single, say, gold nanoparticle as a heavy atom on an AFM probe, as we do. So we believe we could retrieve the phase also with very fast dynamics, okay, in computation, okay. And as we know, nothing is new under the sun, okay. So what we've really done is come to holography by another method where we have holographically combined the emission of an ensom probe, and we have basically used it as a reference wave, in this case a reference tip. It has highly accurate and nanometric stable positioning of the tip, unlike angle of reference waves. It has overlap, like the twin image problem in holography, okay? It has a potential to solve phase ambiguity, and it has, we believe, but not proven, a super resolution potential. What we want to achieve in the future is to be able to rapidly get an image such as you get with an AFM, okay, and be able to get it with the type of resolution that you can, but in parallel, okay? So basically, in HOPS, we have these parameters, that no added parameters, no smoothing, etc., that we have gone over several times. And the paper is actually published, and you all are welcome to look at it. We submitted this paper to Nature, and it was rejected within 12 hours. Okay, so the bottom line is that I was dejected after that situation, and I happened to be giving a talk at UCLA, and one of the children of one of my colleagues at UCLA is now the head of the Nano Center. His name is Paul Wise. And Paul Wise, just as a courtesy, said, I'd like to see you. How are you? How's the family? So I went to see him, and I told him the story. And then he told me, well, Aaron, why don't you send the paper to me? I'll publish it. I said, what? He said, yes. So I said, okay, I don't know exactly what you mean by that, but I'm sending it to you. He's the editor of ACS Nano, and he sent it out to referee. One referee actually came back. Another editor would have said, forget it. He said, this is being published in the wrong place because it should be in an optics journal and not an ACS Nano. He was right, actually. But never mind, that's hindsight. But in any event, one of the, they wrote a review on it, and they say that this is an interesting method. And what they claim, and I hope they're right, that Nanonics et al. In this issue of ACS are providing data for a new era of physics-based imaging and computed imaging. And even though this is not in the nitty-gritty of near-field optics, I thought it's a good place, because you are all interested in imaging, to actually talk about a new methodology that I think may not be the final methodology, but it gives you a new perspective of how important it is to integrate and form a hybrid between an AFM-based tool and a optical, electron, and other imaging-based tools. Because the type of additional information you get has great potential, if used properly, to actually get you much additional information. Okay, so I'll be, of course, glad to answer any questions, but I know we're probably exhausted from all of this, and I thank you for your attention.
I'll step in for Aaron, so are there any questions from the audience here?
Thanks, Mike. So, yes, please.
So, Aaron, the delta function seems to be a key component of this. There are good delta functions and bad delta functions. How good
Yeah, you can use another type of delta function.
But is the probe itself truly the mathematical delta function that you would need?
It is. It basically is a delta function. It doesn't matter how small it is, really. It can't be very big, but it's a sub-wavelength probe, which is actually acting. It's like a quantum dot. Okay. That is used many times as a delta function.
So that's not a limitation on the model, then?
No, I don't think so. We've tried it with different dimensionalities of probe. It's really not the crucial factor there. Okay, so now what I'd like to do is I'd like to invite you all to a reception that we're going to have. But before that, I just see that Hisham just came here, and a lot of you know Hisham.
So you were looking for me.
And I was looking for you because I wanted to introduce you. Okay. So Hisham is, I'm very happy to have Hisham here. I have to say this, Hisham, but what can I say? Hisham has been with Nanonics for many years, and now he's going to join together with a former student of mine, okay, and actually start a company, or they started a company by, and I really hope I wish them a lot of, success, okay. in a totally different area to what we're talking about today. But in any event, we're going to miss Hisham because a lot of you know Hisham, okay? And he was very effective, but we hope to have at least a partial replacement in someone that Hisham has trained for us. But I want to thank Hisham, and I think all of you, many of you have interacted with him, so I think we should give him an applause. Okay, so tomorrow, what we're going to attempt in the morning, okay, is a roundtable discussion on this force issue, okay, and we're going to attempt something which Daria told me I'm really crazy to even attempt, but I'm going to try it, and that is to have a Skype connection. Is there internet in this room by any chance? I mean, there's not.
Yeah.
If this is a little place like Harvard MIT, we have internet here.
Yeah, okay. So that's great news. So someone will help me interconnect.
We
through
can
Skype.
arrange that.
And I even have another projector which you'll be able to see the people from Nanonics, hopefully. But no, don't worry. I brought the projector away. It's not a problem. And I hope it should be an interesting day tomorrow. Very much more hands-on. But really, I really want to thank all the speakers, and definitely Professor Norton and his group, and who really put this thing together. And each of the talks was spectacular, and I really want to thank everyone. Thank you very much.